For the test review of Chapter 4, let me begin with this topic. So briefly, you should know the different names for these families here. They're very commonly used to refer to this entire group, such as alkali metals, alkaline earth metals, etc. And the reason why I started here was just to emphasize that, why do we have this as a group? And what I want to point out is that their chemical reactivity is very similar. For example, all of the alkali metals here, to some degree, react with water when you throw them in, when you put them into water. They're all soft metals, and basically they do this. When you drop them in water, they burn. And there's a similar story for each family that you see on the periodic table here. I don't want to talk about their descriptive chemistry. Instead, I want to focus on one part of their chemistry, and that's the charges that they form. So what you're seeing here is just a small select group of ions that certain elements form. And notice the pattern here. So this first family is always a +1 charge, and I'll explain where the +1 and +2 will show up in a second. Right now it's just sort of recognition of a pattern on the periodic table. +2 on this family. Skipping boron there. There's a +3 state for this group. And then once you transition through the 4A family, the carbon family, then you get on the other side of things, the negative charges. And you can see them here, -3, -2, -1. And you should know these. Notice that the noble gases do not form charges. They basically don't react. Okay. Now this particular charge pattern that you see from the periodic table becomes most important when we start doing nomenclature in Chapter 5. We'll come back to this and we'll use it a lot there. Right now it's just a pattern on the periodic table to know. Notice on the transition metals here, as of right now, there's no elements to be familiar with in terms of specific charges. We'll have more to say about that in Chapter 5. The main point that I want to focus on with charges, how they come about based on the subatomic particles, electrons, protons, neutrons that are in the ion themselves. Okay, and let's just take a couple of these to sort of pick apart. So let's do the magnesium +2 and the oxygen -2. Give us both variations here. Now the first thing I want to look at is actually back at the main periodic table. And I want to focus in on the 12 on the magnesium and the 8 on the oxygen. So those numbers, we learned, referred to as the atomic number. And that represents the number of protons in the nucleus. That essentially identifies the element. So for example, any atom with 12 protons will be magnesium, no matter what else is happening to it. Any element that has 8 protons is going to be oxygen, no matter what else is going on with it. Okay? That's important to understand. So if we think about just a normal, neutral, elemental form of magnesium, this would be that. It would be a soft metal. All right? We saw it in one of the videos. We saw in Lab 3 where it burns in the flame. Now we already know that it has, so let me just use P as proton, E is the electron. We already know that it has 12 protons because sort of by definition, that's what magnesium does. It just has 12 protons. If it doesn't have 12 protons, it's not magnesium. Now, since there's no charge on this particular atom, this elemental form of magnesium, then it also has 12 electrons. Now, the way that it goes from the elemental state to the ionic state, it takes on a +2 because we just saw that. It always takes on a +2. To go from the elemental state to the +2 state, it's not the number of protons that's going to change. Right? If we have magnesium, we always have 12 protons. What happens is there has to be a change in the number of electrons. So we learned the electrons are on the outside of the nucleus. Those are the things that are accessible for chemical reactions. And these are what changes during a chemical reaction. And this is what's happening. This is a chemical reaction. So to get a +2 state, what that means is that we had to have lost 2 electrons in the process. Sometimes this is written in that form. Now notice the formula down here. If you take the number of protons, subtract the number of electrons, you're going to have the charge that's on the ion. Right? You can think of this way, what do protons have? Protons have a positive charge, electrons have a negative charge. Combine those, and that's where you get the +2 state in the magnesium. Now, for oxygen, it's a little bit different story. We've already said that it has 8 protons, and just like before, let's imagine this is the elemental form. That means that it would have 8 electrons as well. Well, when it goes to what we call the oxide anion, it forms a negative 2 charge. And again, in some ways, it's just a pattern that forms on the periodic table when we sort these elements out the way we do. Well, if it's oxygen, again, there's still just 8 protons in there. That doesn't change. The charge that we account for here the charge that we see here has to be accounted for changes in the electron. In this process, it's actually gaining the number of electrons. It's going from something that's neutral to something more negative. It's gaining electrons. How many electrons? Well, 2. So on this side of the periodic table, all of these will add, these gain electrons when they go to the ionic state. And then, this is sort of a convenient divider line. And then on this side of the periodic table, we'll see it with the transition metals as well. These lose electrons to form cations. Right? These gain electrons to form anions. And then in chapter 5, we'll bring these together, form salts, nomenclature, etc. Like, for example, a few labs from now, when we're determining the empirical formula for magnesium oxide, it's going to be MgO. For every 1 magnesium cation, you need 1 oxide anion to balance out those charges. And so they come together in the simplest form. This is what we'll start doing in chapter 5. Now notice here, I said nothing about neutrons. Neutrons have no charge, and so they don't affect the overall charge of the ion. Honestly, you could have as many neutrons as you want here in a way, and it's not going to affect the charge. How do we factor in neutrons? Well, we saw this is where we bring in the mass number. So that equals the number of protons plus the number of neutrons. So like, for example, if we just want to pick one of these apart, we do the classic kind of number of protons, electrons, neutrons. It's neon, so we look at the atomic number. That means there's 10 protons. There's no charge indicated, so protons and electrons are equal, so that's 10. The number of neutrons, that information is up here. And basically what you have to do, you can imagine, subtract these two. 22 minus 10, and you get 12 neutrons in this particular isotope of neon. 11 neutrons here, 10 neutrons there. And we're ready to fill out a chart like this. I'll do a couple rows, talk about each one a little bit, and then I would encourage you to pause the video, try to answer the rest, and then play the video to see the answer. Okay, the 2 that I want to work through is that one and that one. Let me just take a look at this one first. I always like to focus in on the number of protons, right? Because what that does is it tells me what element I'm dealing with. So it starts putting in a lot of notation in a chart like this. So 82, let's go back to the periodic table. Where is 82? 82 is right there. So we're dealing with lead in this example. So the symbol, well, we don't know, if there's a charge yet or not. We know what the symbol is there. The Z and the A, Z and the A. So the Z is going to be the atomic number here. These two are equal. Atomic number of protons are equal. Now notice in the problem, it's telling us all of the subatomic particles in this row. That tells us everything about the atom, the ion, whatever we have here. Like, for example, let's just go ahead and knock out the ionic charge on this thing. Again, if you can imagine the math, what charge do the protons take? Plus 82 minus the 80 electrons. So this has a plus 2, or, I guess, let me just stick with the typical convention, 2 plus charge. I think the reason why chemists put the positive charge and the negative charge on the back end is to make sure that you're not thinking that it's like a addition or subtraction. I don't know. Anyway, that's the convention. That is not a typo here, by the way. And then the last one to worry about is the mass number. Right? Remember, that is adding up protons and neutrons, right? It tells us what the mass is for the atom. It tells us what the number of particles are in the nucleus. Add those two together, 207. Now, there's one other little feature that you want to add here. When you have a charge on your ion, then you always include it in the notation. So the other one I want to do here, so some of the subatomic particles are missing, okay, but we do have this information. Like I said, atomic number equals the number of protons, so 22 protons, put that there. Notice that the number of protons and number of electrons are not equal, therefore we do have a charge. So again, imagine the math here. Protons carrying a positive charge, electrons carrying a negative charge, 22 minus 18 gives us a 4 plus charge on this ion. Number of neutrons are missing, but we do have the mass number here. Remember the way we determine the number of neutrons. If we have the mass number and the number of protons, imagine it's sort of an old school subtraction problem. 22 minus 10. Mass number minus the atomic number. Mass number is 48 minus 22. That's equal to 26. And the last thing, the symbol here, and I could have done part of this early, so look for element number 22 back on our periodic table. It's titanium. And then the titanium's taken on a 4 plus charge. Okay, go ahead and pause the video, work on the other 3 lines, and then once you restart the video, you'll see the answers to all the blocks there. So there are the answers. Now, there's one thing I just want to point out here, and it's not terribly important, but you may be wondering about something. Why am I not showing the neutrons in the symbol here? Well, typically, if you have an ionic substance, if you have an ion, you omit the neutrons. Okay, so actually, I should say you omit the mass number in ions. Really, the only time you see the mass number show up, i.e. information about the neutrons, is when you're working with a neutral atom like this, an isotope, your typical isotope. Occasionally, a few textbooks, a few websites will do something like this. So let me just use the lead as an example. They'll show the charge, and then they also show the atomic number and the mass number. That is not incorrect, but this is rarely used. Okay, and we certainly won't use it in this class. Again, if we have an ion, we're trying to emphasize the charge. The charge is what's going to dictate its chemical reactivity. The number of neutrons are irrelevant, and so we just do this. Right? We omit the mass number when we're dealing with an ion. And then the last topic I want to cover in this review is the calculation of the average atomic mass for an element. So what this problem is telling us is that magnesium, it doesn't just have a single isotope. There's actually 3 isotopes that are naturally occurring on this planet. And it's those isotopes that dictate the average mass of the element. So that problem, you'll have a periodic table for the test. That particular problem, we have a periodic table in front of us. We actually know the answer, okay? We just want to see how we get to that answer. It's at 24.31 as the atomic mass for the element. That is an average, what we call a weighted average for all the different isotopes that are present on this planet for magnesium. And that's what you see in the problem. And just to expand a little bit on this particular problem, and you don't even have to do this to do the calculation, but I mentioned there are 3 isotopes. Let's just write those down real quick. Okay. Like for example, 23.99, that's pretty close to 24 atomic mass units. Remember, that mass is represented there is really describing what's in the nucleus. So there's 24 particles in the nucleus for magnesium. Magnesium has atomic number of 12. So the first isotope has that isotopic notation. Round this one up, that's 25. Round this one up, that's 26. So it shows us the total 3 naturally occurring isotopes for magnesium on our planet. These masses you see here are measured in the laboratory, okay? And so are the percentages here. And so what we see is that, well, this particular isotope is coming in at a higher percentage, much higher percentage. And the other two are coming in about 10% each. The isotope that's coming in at the highest percentage is the magnesium-24 isotope. That's reflected on the average atomic mass value on the periodic table, which was 24.31. All right? So basically, all of the average atomic masses here basically represents what's the most common isotope on the for a given element. It's not always the case, but that's the general rule of thumb that we use here. Okay, so how do we calculate that 24.31 AMU from the periodic table? Well, the first thing we do is we want to convert the percentages to a decimal. And all you do there is you divide by 100. So what it's going to do is going to push the decimal 2 places over. You take each of these values and you're going to multiply it by their mass. So basically what you're doing is you're adjusting the contribution to the average based on the mass and then this particular percent of that mass. So just do it a step at a time. And then you're adding up each one of these products. And I'm dropping the unit there just for convenience. And like all calculators, when you do a calculation like this, it gives you more digits than you can use, okay? So we have to factor in our Sig Figs in this calculation as well. You just got to watch out because you're doing a multiplication step and an addition step. And there's 2 different rules that we learned back in Chapter 2 for dealing with the Sig Figs here. Like for example, if I look at this, and you just take it a step at a time. Multiplication here. 4 Sig Figs, 4 Sig Figs. And so if you were to apply the Sig Fig rules here, it would tell you that, okay, I want to keep 4 Sig Figs there. Same here. Now this one's a little simpler because, well, this is just 0.1. But you still, I'm applying the Sig Fig rules correctly. 4 Sig Figs, 4 Sig Figs, and then it tells me I would keep those first 4. And the addition rule, the way you use that is you say, well, how many decimals am I looking at? So I have 3 decimals here, 3 decimals there that are significant, based on the first rule. And there's only 2 decimal places here. So when I add this together, let me just go ahead and do that. So when I add these together, I do get that 24 and some change there. And I just said, okay, I've got to keep just 2 decimal places based on that final significant figure rule for addition. So it's those 2 that I want to keep. So that next digit down is, 5 or greater, you're going to round. It means that you're going to round that one up. And so your final answer, like I said, we already knew this answer based on the periodic table, but that's what you go through when you do one of these calculations. Thanks.